So our line won't ever stop.
Okay, continuing with chemistry. We are going to have a number of woo clap questions. Amy was really excited to do these while I was preparing the lecture this morning.
That makes them even better.
Does that mean that we can email her for the answers? Yes.
I don't think she would remember them.
Oh.
I don't think she'd respond.
I don't understand how this is.
Well, she was saying them out loud to me, so.
Oh, okay.
I'm on Google Class.
Aggravated.
Nice.
I did. It said you couldn't stop, so I'm getting aggravated.
Cannot stop.
Okay, so today is February 28. Tomorrow is February 29, a leap day. We're going to cover astronomy later in the semester, but I thought this would be a great time while you're getting this up for us to talk about why do we have leap years and leap days? How many days do we have in a year?
365.5.
Okay, we have 365 days in a standard year. But we're not the ones who actually set the length of the year. The length of the year is set by the time it takes for the Earth to do one orbit around the sun. And the time it takes for the Earth to do one orbit around the sun is 365.2422 days. It's not an exact fraction, right? So if you go back to the Julian calendar, before the Julian calendar, they had calendars that did all kinds of funky things to try to match the seasons. But the thing you want is you want a calendar so that the beginning of the year is always in the same season. So the Julian calendar, they recognized that there was more than 365, less than 366 days in a year. So they added 1 day every 4 years. So if you add 1 day every 4 years, what's the average length of the year?
365.5.
Well, if it's 1 every 4, you added a quarter, so 0.25. 365.25. So that's what the Julian calendar did. They had a leap year every 4 years. Those crazy, ignorant people, right? So what do we do now? We don't follow the Julian calendar. We don't have a leap day every 4 years. How many of you knew that we don't have a leap day every 4 years?
I feel like I kind of knew that, because I feel like we haven't had one in 8 years.
Well, we've actually had one every 4 years in your life, and in my life. But we don't have one every 4 years, because that would make the year just a little bit too long. It'd be 365.25 instead of 365.2422. So what we do is we skip a leap year every 100 years.
That's lame.
So every year that's divisible by 100, we skip the leap day. But the problem there is, then you're subtracting, you're subtracting 0.1, so the average day would be 365.24. That's too short. So you went from one side to the other. So if the year is divisible by 400, we don't skip leap year. So the rules are a little convoluted, but then you're adding in 0.0025. And so with our Gregorian calendar, that's the calendar we're on, you have a leap year every 4 years, except for skip it if it's divisible by 100, except for add it back in if it's divisible by 400. And that gives us an average year of 365.2425, which is really close to 365.2422.
Basically, our solution was, let's make it so we're not dealing with the problem next time.
Well,
Is what it sounds like.
no, in fact, we did deal with it. In the year 1900, they did not have a leap day. You guys very well may live to the year 2100. There won't be a leap day in 2100. But in 2000, that was divisible by 400, so they added it back in. So none of us have so far lived through a year where it was skipped.
80 years from now.
Yeah.
You think I'm going to live another 80
I think you'll live to be 100,
I'm not gonna
Jessica.
live to be 100. I'm just telling you.
already.
I'm
I have faith.
dying at 60. I don't even care.
Okay,
I'm a hypochondriac. I'm
You
like
guys
already
are
thinking of dying.
I hope you're all connected by now. So let's get going with more chemistry. So our focus today is on two fundamental things: the difference between a chemical change and a physical change, and how to name chemical compounds. So a physical change, and we're going to have to answer questions in lab on physical changes. A physical change is a change in physical properties only. If it has chemical change along with a physical change, we're going to call it a chemical change, okay? So physical change is only a change in physical properties. So what is a change in physical properties? It's if something looks or feels different. Chemical property is when you actually change chemical bonds, the bonds between atoms. So chemical changes, you may have started with, sodium chloride, you end with something else. Yes, Alex.
Would ice melting be an example of a physical change?
Ice melting is a physical change. It's one of the examples I have in my upcoming slides, yes.
Okay. Yeah.
So,
Wait,
excuse me?
more. I need 2 more words.
How do you spell
So,
focus?
thank you.
I spell what?
Never mind.
I needed 3 of them. Thank you. I'm good.
Leave it over. Sorry.
Yeah, alias is A-L-L-I-U-S.
A-L-I-A-S.
A-L-I.
Alright, we're good.
What's the one that you said is both?
Well,
Thank you.
if it has a chemical change, it's going to have physical change as well, but we call it chemical change if it has a chemical change.
I thought
So-
there was a tricky one.
Hopefully, no. We try to avoid trickery as much as possible. So here's examples of physical properties. You have opacity, if something is transparent or not. So glass is transparent, gold is opaque. The color, gold has a yellowish color. The phase is like, is it solid, liquid, gas? And then density, that's another physical property. So these are all physical properties. Another example here, diamonds, they're transparent. They have no color unless you put impurities in them, then they'll have color. Just like sapphire, once again, is transparent and has no color unless you put impurities in it. What color do you think of for sapphire?
Well, it's supposed to be white, but you can get blue sapphire without any transparencies.
Okay. You can get blue sapphires, or you can get,
Green
I want purple.
and pink.
the most common one is pink, and they have a special name for it. If it's a pink sapphire, they call it a ruby.
Are you sure?
I'm positive. I did my master's research on this.
That's so cool.
So I was working with pure sapphires, so they were transparent. They had no color.
Maybe that's cool.
Phase, solid, density, 3.5 grams per milliliter. Notice the diamond is far less dense than gold. Gold is a very dense material.
Does that mean that it's heavier? I know that's a really dumb question.
But yeah, if you had a diamond and a piece of gold that were the same size, the gold would be like 5 times heavier.
Just making sure, because
I have a question. Then when you have like partial gold jewelry, like 18 karat gold and stuff, why does it bend easier than other gold?
I don't know what they're using in the alloy, so I just don't have an answer.
I'm just curious if it's because they only use partial gold and so it's not a
Yeah,
full.
I mean, if it's 18 karat, it's partial gold and it's partial something else. And
Right.
I don't know if it's silver they mix in or what they even mix in.
So when they do like 10 karat, that's why it's so hard and it doesn't bend at all, is because it's a higher carat.
The physical properties are going to change with the alloys, and I simply don't know
Okay.
what the alloys are. Water. Water is transparent, has no color, hopefully. Phase is liquid, density 1 gram per milliliter, right? These are all physical properties. They're just examples of physical properties. Here is a chemical change. You have this car and it's rusted, right? The iron doesn't look the same. It's been chemically changed by rust. Rust is an iron oxide. That is a compound with iron and oxygen bonded together. And so it's a chemical change going from iron to iron oxide. It also looks different, but we're calling it a chemical change if the physical change is the result of a chemical change. Because that, in the lab, that's always an area of confusion. It looks different, and it's a different chemical combination. Which one do I call it? So what's the answer? Which one do you call it if it both looks different and is a different chemical compound?
Chemical one.
Right. Now, physical changes, and here's the example that you brought up, I think, Alex. You have liquid water and solid water. Liquid water we call water, solid water we call ice. They are the same chemical. And so going from liquid to solid, solid to liquid, that's a physical change because you definitely would describe ice and water differently, but they're chemically the same. The other example here is kind of esoteric. It's a boiling versus non-boiling mercury, it says. Now, mercury is silver looking, so you should be able to see the thermometer if it was actually mercury. Clearly, these pictures were with water. But the mercury, the boiling mercury would, okay, they're looking at the mercury in the thermometer. That's why the mercury, because it's got to be water. But the reason we use mercury or used mercury in thermometers is because the mercury expands a lot when you heat it up. So that's a physical change when it expanded. So it looks the same, but it has a different density because of that expansion.
Do they have like food coloring or something to it?
Well, no, what they use now is food coloring in alcohol.
Oh, okay.
So it's not mercury, it's alcohol with food coloring. Because otherwise, hey, look, it's clear all the way through. What's the temperature?
Yeah.
Go for it. These are examples of chemical changes. Here you're having a burning gas. That gas starts out as something like methane, and I'll show the reaction, I think on the next slide, for the chemical reaction that's going on with methane. But that methane is oxidized. It's basically the same as rusting, except for it's not iron. And it produces different chemicals, as well as, obviously, it looks different. Feels different because you're not going to get burned with the nice, cool methane, but you're going to get burned with the flame. The next one is you mix vinegar and, I should have done this. That would be easy enough to do. Mix vinegar and baking soda. And it goes, psh, and you'll do some of that in lab. And so that's a chemical change because you're forming carbon dioxide and water when you mix them. And the final one here that is showing is copper oxidizing. Oxidizing is the same as iron oxidizing to make rust. So you could say that this is what a rusty copper looks like. Not nearly the same as rusty iron. We don't call it rust. We call it rust. It's iron oxide. Why is Mars red?
Because of all the iron.
Iron oxide. It's all the rust on the surface. So here is the actual what's going on with chemicals when you burn methane. So methane is this thing here. See the black? That black is supposed to be a carbon atom, and we use its element symbol C. And then it has, you see these blue things, those are hydrogens, so it has 4 hydrogens on it. And so this is how we write methane. Or we can write it as a chemical formula, CH with the subscript 4. That subscript means that there are 4 hydrogens attached to this molecule. So that's the methane. Up on top we have 2 different water molecules, or oxygen molecules. So this here is an oxygen. The red is an O, so that's 2 O's, O2. Now, if you bring these together, nothing happens until you add heat. When you add heat, the heat will cause those molecules to break apart. And then when you have those molecules broken apart together, they will form a lower energy combination that is 2 waters. What was the red atom?
The oxygen.
Oxygen. So there's an O there, and then what was the bluish ones?
The carbon.
Carbon.
Not the carbon. The carbon was the black center.
Oh,
They were the hydrogens.
yeah.
So that's water, H2O. And then this here has the carbon in the center with an oxygen on each side. Now it turns out these are what we call double bonds. It looks a little different. That's carbon dioxide. So we're going to learn these naming rules as well. So there's a lot of new things to learn here in chemistry. But that's how the reaction occurs. You have to add heat to make this occur. Add heat. Do you remember heat from our physics discussion?
Doesn't it like make
Things are
stuff
faster.
excited or something like that?
Okay, heat was a transfer of energy.
Energy is
And if you
faster.
raise the temperature, they go faster.
Yeah.
And they go faster, they bang off each other, and they break apart. Okay, so I think this is my final slide on determining physical versus chemical properties. A physical change imposes a new set of conditions. That is, it's got a different texture, a different color, a different density. Those kinds of things are physical changes. A chemical change is the chemical bonds have been altered. So you have different chemicals involved. Same atoms, but different chemicals. And if you have both, then it's a chemical change. So both physical and chemical changes result in a change in physical appearance. But if it has a chemical change, we classify it as chemical. If it doesn't and it has a physical change, we classify it as physical. All right, so our first clicker question. Melting a piece of solid, pure gold, what kind of change would that be?
I got you. Voting's closed.
Voting's closed?
Yeah.
You're right. Okay, start now.
Oh, man, I said no.
1, 2,
Hold on, I got it. Hold on.
4. Everyone's answered.
There's
No,
five.
You're right. I fail at math.
It's my bad.
Well, not necessarily.
Okay. There we go.
There we go. Okay, so our answers were, I press the wrong button all the time, 4, 0, 1, 0. This is good. It's a physical change.
Yeah.
It still was pure gold. It didn't change the chemical bonds. It's the same as melting ice to make water. Physical change, not a chemical change. Vocab words, elements and compounds. The first word here is element, but I'm going to define them both on this page because compound comes up later, but it doesn't have its own definition page. Element, if something is an element, it's only one kind of atom. So pure gold is elemental. It's just one kind of atom. Or if I have pure oxygen is not O's, it's O2s. We call a combination of atoms a molecule. So I'm going to write molecule is a combination of atoms. So oxygen is 2 oxygen atoms bound together, O2. But that's still elemental because it has no other types of atoms, only one type of atoms. So O2 is an element. It doesn't have to be everything's a single atom by itself. So molecule is 2 or more atoms that are bound together. If they all have one type of element, then we say it's elemental. If they have, actually I do have compound described differently. It was molecule that I didn't have described differently, I think. So what is an element? You tell me.
A material that's made out of one atom.
One type of atom. Not only one atom, but only one kind of atom. Okay, so here are some examples of elements. If you have pure oxygen, it's O2. If you have ozone, it's O3. Both of these are elemental oxygen because they only contain one kind of atom, oxygen. So they're both elemental oxygen, but they're actually different things. Ozone, you've heard of the ozone layer, right?
Yep.
We're going to talk about the breakdown of the ozone layer later with our chemistry section, but it's something that's important to us, that ozone. Ozone is actually very interesting in that it is a highly constrained triangle, whereas O2 is oxygen bound to oxygen with what we call a double bond. Sulfur, S8, elemental, only one type of atom. Gold, AU. AU, what is it? Oricium is gold in Latin. Yeah.
So does for the ozone, like, if it's happening in the atmosphere,
Mm-hmm.
is one of the, whatever the word is, the O's, is it like coming apart and then becomes an oxygen like the O2?
Right, it breaks and then becomes O2.
Yes, so that's what's happening.
Yeah.
So that's why there's rising sea levels.
No, different thing.
But I thought that since oxygen, then it would be like, rain. I don't know what I'm saying.
Well, when we talk about like the greenhouse effect, that's not really ozone related. So they're two different things. They're both important. And we will cover, actually, I think both. Yes, Alex.
What is the letter next to the O called?
Letter next to O.
Or
The number?
Number, yeah.
That is telling us how many are present. I don't know a name for it.
I was hoping I could.
I mean, you can say it's a subscripted number, but it's not a name. It's a description.
So it has nothing to do with the electrons?
No, it doesn't. All right, so those are different elemental molecules. Now, a compound is when you have more than one type of atom. So every chemical is either elemental or a compound. If it's one type of atom, it's elemental. If it's more than one type of atom, it's a compound. So here's some examples. Sodium chloride, Na's and Cl's.
Yes, salt.
It's salt, table salt, or halite. This here is ammonia, NH3. It has N's, nitrogens, and hydrogens, H. So it's a compound, not elemental. So the distinction between those is pretty simple, but they're both molecules. They're both examples of atoms bound together. So do you have those words, element, molecule, compound? Can you keep those straight?
I can try.
I can try. That's
So,
been helpful.
So nitrogen has a -3 charge?
Nitrogen typically is a -3 charge, yes.
Okay.
You must have studied a little more chemistry because that's not something I've talked about yet.
Yeah.
These are showing examples of how you can go from a sodium metal and a chlorine gas. This is elemental for both of these. And then reaction to form a compound, sodium chloride. Here's something I have never done. When I was gone on choir tour, my teacher took some of my classmates down to the beach and threw a chunk of sodium into the ocean.
Oh.
Sodium is cool because it reacts really strongly with water, so basically blows up when you put it in water. So they store it in kerosene, I believe it is, so it won't blow up.
All right.
Yeah, that just doesn't seem right, does it?
I want to see that.
I do too. I mean, you can watch YouTube videos. There's actually, so Sodium is in the first column. What do we call the first column of the periodic table?
That's the high column, right? That's the higher
Alkaline?
one.
They're the alkali metals. The second column is the alkaline earth metals. So those can be confused easily. So those alkali metals, all of them, except for hydrogen, are going to go kablooey when you put them in water. And so you can find a YouTube video of guys using high-speed cameras and recording the explosions where they put lithium in a bathtub of water, sodium in a bathtub of water, potassium in, rubidium.
Cesium.
I think they went to cesium, which is radioactive.
Wow.
I'm not sure if they did or not, but it would be kind of dumb actually to do cesium because that's going to make a mess. So maybe they did. But it's really interesting to see the explosions and see them get bigger and bigger. Okay, here's some examples of compounds. Sodium chloride is NaCl. Ammonia we'll call a common name.
Are we going to be balancing equations?
We will eventually, not today, but we will eventually. And water. Water is also a common name. Now we are going to learn on the next slide how to give these standardized names. So some things we'll call by common names, some we'll call by standardized name. Water, we're always going to call it water. We're not going to use the standardized name. We'll use the common name. So how do we name things? We have 3 guidelines. Here's guideline number 1. No, this is easy. You might have taken a higher level chemistry class where it got hard, but this is not going to be hard. So you start with the element farthest left in the periodic table. So in the example of sodium chloride, which one is farther to the... I just gave you the stupid name.
It's okay. NaCl.
Na is farther on the left than Cl is. I actually have a slide for that. Look. Na is on the left, Cl is on the right. So you're going to use the sodium first. And then you just name the second one and add I to it. So instead of sodium chlorine, it's sodium chloride.
But there's some that have sulfates.
We have 3 guidelines. We have 3 guidelines. We're not going there. We're not going to the sulfates and sulfites.
So much.
Somebody's going to be bored of this section clearly. She's had more chemistry than we're going to cover. So let's go back to this slide. The top one's already named as sodium chloride. What would we call NH3? What is N?
Sodium
Hydrogen
chloride.
nitride.
Oh, I'm sorry.
I thought you said start with the one that's farthest to the left.
We normally do. This one here breaks it. H's don't follow that rule.
Okay.
I'll write it that way so hydrogen, spell hydrogen right. Nitride. Now here's something that is rule 2 or rule 3. Rule 2 or rule 3, one of them, well, let's just go forward. Rule 2, with different possible combinations of the same elements, use prefixes to remove ambiguity. So with this one here, with NH3, I don't know, well, I do know, you can have NH3 or NH4. One of them is an ion, but it still exists. One of them is ammonia, one of them is ammonium. And so we'll put here a prefix of tri to say there are 3 hydrogen and 1 nitrogen. So ammonia could be called trihydrogen nitride. And water, what would you call water with the same rules? Which one is farther to the left? Okay, which one has 2 of them?
Hydrogen, so dihydrogen oxide?
Yes, dihydrogen, and we say monooxide because there's lots of combinations available. If in doubt, put all the prefixes. I won't mark you wrong if you put a correct prefix and it wasn't necessary. But I would mark you wrong if you didn't put the correct prefix and it was necessary. So dihydrogen monoxide would be the standard name for water, but instead we use the common name water. But you do need to be familiar. If I say water, your brain has to say, oh yes, that's H2O. What does it mean, H2O? It means two H's. That subscript means how many of the preceding element there is.
2 hydrogens, 1 oxygen.
Excuse me?
2 hydrogens, 1 oxygen.
Yes. Okay, so we have our rules. The third rule is common names are sometimes used for convenience. So they're also acceptable names. So here's your prefix list as far as we're going to go. Mono for 1, di for 2, tri for 3, and tetra for 4. So you ready for another quiz?
No.
Okay, then somebody is. Let's do some practice and then we'll do the quiz. So what would you call CO?
Carbon, no, because CO2 is carbon dioxide.
So
Carbon oxide.
Carbon monoxide?
yes, carbon, and we don't double the O, we just put monoxide.
Duh. That was really dumb.
So that's carbon monoxide. What would the lower one be?
Carbon dioxide.
The lower one, carbon dioxide, because it has 2 oxygens instead of 1. And then we already did this one here, dihydrogen
Oh yeah, dihydrogen.
monoxide. And what about this one here?
Dihydrogen.
Dioxide?
Yes.
Because 2, so it's always going to be di because of 2. Right?
But these both have common names. So what's the common name for H2O? Water. And then there's the joke. 2 chemists walk into the bar. The first chemist says, I'll have a glass of H2O. And he drinks it. The second chemist says, I'll have a glass of H2O2. And he gets it, and he drinks it, and he dies.
Peroxide.
Because it is hydrogen peroxide is the common name for this. Dihydrogen dioxide is more commonly known as hydrogen peroxide.
So he was saying H2O2 also.
Yeah, he meant also, and the bartender gave him hydrogen peroxide. It's good. Okay, maybe it's not a good joke. It's a joke. I know there's 2 types of jokes and good jokes, but so now you feel more comfortable with the naming?
I'm still ready to know.
Let's just get her over with.
Get her done.
Oh.
Okay, so here is our next one. What is the name of the compound with the formula CBr4? And just to make it clear, what is C? What does that stand for?
Carbon.
And what does Br stand for? Bromine is what Br stands for. Okay.
I prefer bromine to bromine.
Yeah.
Okay. Excellent. We are doing well today. Everybody, 5 out of 5
No way.
said carbon tetrabromide.
We got our first one all right.
We all
Are you gonna bring us a treat on Monday?
probably should.
Yeah. I really think you should. It's the first time. Probably the
Now-
last. Just kidding.
Why do we have tetra here?
4.
4. Was it necessary? You weren't sure, right? And so you put it there because you weren't sure if it needed it. There might have been no other combinations with carbon and bromide. I was looking this up before class, and you can use the name carbon bromide for this as well. The standard name that's used is carbon tetrabromide. But there are no other carbon bromides that I could find. So carbon bromide, I did find somebody who was selling and calling this carbon bromide. So that would have been an option. That would not be wrong. But this one here, you know you're right. I was laughing when I was doing this. The top one really cracked me up. Carbro 4. And the second one, Sieber 4, like you just read it. It's kind of funny. So I was laughing. Amy's like, why are you laughing? All right. We have naming of compounds, and we have the difference between an element and a compound. What is a compound? Two types of atoms. A molecule is combined with atoms. Compound is two types of atoms in a molecule, or more. And so what is an element? One type of atom in the molecule. So now we're actually going to start talking about bonds that form. I like Vanessa's attitude these days, huh? So, atoms bond together because of their electrons. It's the electrons that give us the chemical properties. So remember I talked about how Dmitry Mendeleev organized the atoms by how they make chemical reactions. And what that means is he organized them by their electron structures. So the bonds are based on the electron structures. All of the bonding has to do with electrons. It doesn't have to do with the nucleus. The nucleus is only important to the chemicals insofar as it gives you the electron structure. So, the electrons are really important. We have to know something about them. And we talked about those shells in the lecture on Wednesday. Remember that was where we ended Wednesday? So here's the picture again. I know, it's hard to remember. Here's the picture you weren't. Here's the picture with those shells. So we're going to be dealing with this idea again. And you recall, we even talked about how the electrons are shown. We had the whole first couple rows of the periodic table showing the shell filling of different atoms. And I said we're going to see why we have like the unpaired sometimes and paired sometimes electrons. So this here is all just, we've already looked at all of this. Now we're going to see how that's important in chemistry. Okay.
Sorry, I got very excited.
I'm glad we can get excited about stockings.
We should get you some fun ones, Dr. Webb. Would you roll your pants up so we can see them if we did? No?
Probably because I do dumb stuff. But electron dot structures. You're going to have to identify electron dot structures on the next test.
Oh.
It's not hard. It's not hard.
Exactly. That's why I was shaming you for being excited.
The ones that are just the one dot that combines with the other one, right?
We'll get there.
Okay, I'm just asking because I don't remember anything.
Yeah. They have to do with how it bonds. But first of all we show is the outermost electrons. Remember, in these structures we had, like for the third period, we had 3 shells there. But the inner shells aren't participating in the bonding, only the outermost shell. So when we do the electron dot structure, we ignore everything but the outermost shell. So if you come down to, let's say we're looking at bromine. So here's bromine. Bromine has 35 total electrons. How do I know? Because it says in the upper right-hand corner how many protons, but you have the same number of electrons. But the first 18 are buried. So all we worry about is the outer ones. Here's another cool thing. We skip these. So as far as I'm concerned, all I'm going to draw for bromine is I have 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. I skipped everything from the rows above, and I skipped everything that was in these transition metals. So all you have to do is look at the periodic table and add up.
Oh, okay, I get it. Wait, but why do we skip the ones in the middle?
Why do we skip the ones that? That's
We.
a little complicated.
Just gives me.
Because these are actually belonging to this shell.
Oh, okay.
We draw them as if they're in this shell, but they don't belong there.
How blind are you?
Blind?
Yeah.
I'm not that blind.
So we would have 7
I'm not.
in the outer shell with bromine. And so how do we arrange those is the next question.
One, the 2 and the far side.
On the outside.
I don't know.
So you put them like this. So here's Br. How many electrons am I going to put with bromine?
Okay, I'm gonna stop.
How many people on the right? How many electrons am I going to put with bromine? You're on the left.
7.
7.
Thank you.
So I'm going to put,
On my right.
so that's 7 valence.
We're sorry, Dr. Bud. It's a Friday.
7 valence electrons. Those are the electrons that are going to participate in bonds potentially. The core electrons are all the other ones that we skipped. So where do you suppose I should put the first one? Just guess. Where should I put the first electron?
On the outermost shell.
Okay, we're only doing the outermost shell. Where should I put it with regard to this bromine?
Right side.
Okay, that's what I do. Then the next one, that was kind of a random decision, right?
Does it matter?
The next one, I'm going to put 90 degrees from it. The next one, 90 degrees from that. The next one, 90 degrees from that. Now I have 4, right? But if I go 90 degrees, I'm going to double up. Go 90 degrees, double up. Go 90 degrees, double up, and there I'm done.
He's done.
So I have 2 pairs of 2 and 1 lone electron. If I'm going to bond with something, that 1 lone electron is the thing that's going to be bonding. So this could have 1 electron that bonds with something else. Now compare that to carbon. If you look back there for carbon, where's carbon on that? How many valence electrons will it have?
6. 14. What's that? I'm sorry. Ask the question.
How many valence electrons will carbon have?
Carbon?
You skip the rows above it.
3.
So far we haven't had the correct answer.
Oh, 4.
It's 4. You skip the rows above it, so you skip the hydrogen helium, and then you only
Oh,
count
yeah, it's 4. Yeah.
1, 2, 3,
I just
4.
can't count because I'm an idiot.
Not
I
an
had
idiot.
the right thing in mind. I had the right thing in mind. I was
Okay.
counting 1, 2, 3.
So the carbon is going to have 4 electrons in its valence shell. 4 valence electrons.
Spray. Sugar. Yeah.
So where do I put my valence electrons on the carbon? Where should I start?
On the left.
Okay.
That's the only ones I got, guys.
Well, no, it doesn't matter. It was arbitrary choice.
I know, that's why I
That's
didn't back.
it. Couldn't be. Okay, so where do I put the next one?
On the right.
I go 90 degrees.
On the bottom.
90 degrees. 90 degrees. And I'm done. How many bonds can this carbon make? How many lone electrons does it have?
It can make 4 bonds.
It can make 4 bonds because it has 4 lone electrons.
Wow.
That's crazy.
It is crazy. I agree. So look, here's the examples we just did, except for we did bromine instead of chlorine. But what's the difference in bromine and chlorine? Look at the periodic table. Where are they with relation to each other?
Completely different rows.
But
What was the
On the
question?
same side of the periodic table.
not just on the same side. The relationship between bromine and chlorine in the periodic table.
I have to do it.
They're in the same group.
They're in the same group. Chlorine is directly above bromine,
Okay, who
which
raised-
means that they are going to behave the same chemically for the most part. They have the same electron structure.
I'm an idiot.
No, you're not. You're not supposed to have it memorized, so it's easy to make those kind of mistakes.
You would be such a good dad.
Is he not a dad?
No, I'm just saying, like, my dad, if I was like, I'm an idiot, he'd be like, yes, you are. I'd be like,
If I make a mistake, I definitely do it again.
Well, if a teacher says you're a moron, that teacher probably shouldn't be a teacher, right?
Me. Don't you dare switch it.
Don't I dare.
Okay, you can now.
Okay, so notice
I saw
the bromine. Now the bromine had its,
He's getting trigger happy. He's getting trigger happy.
the way we wrote it, we had the bromine with its only lone electron at the bottom. Who cares? It still had one lone electron and 3 pairs.
Next time I'm feeling lonely, who cares?
Well, no, it's about where you're lonely. We don't care if you're lonely at home or lonely at, okay, we do care.
Who cares?
But for chemistry, we don't care which side we put the lone one on, just that it has it. So those unpaired electrons are the things that are going to participate in chemical bonds. And remember, we call the outermost shell the valence electrons. I was writing about them on the previous slide, talked about on the previous slide. This is where I have the word there highlighted to make sure you remember this is a vocab word we need to know.
You say this.
I say this.
Mm-hmm.
So the electron dot structure. We, of course, want to see how that's useful, right?
Yes.
Apparently not yet. Special note, if you have something that's in the noble gases, like krypton or xenon or radon or argon and neon or helium, those have a complete outer shell. The valence electrons are completely filling every option. They're all paired up. And because they're all paired up, they're not going to form chemical bonds with anything. So those are the noble gases or the inert gases because of their electron structure having all the valence spots filled. So once again, here is the important parts of the periodic table for this electron dot structure. Notice it's skipping the transition metals. Well, the transition metals don't start on that row. They start here. But skipping the transition metals and showing the electron dot structures. And you notice that the first period is on the right-hand side. The neon is different because it does. In the first period, you can only put in 2 electrons. That's why helium doesn't look like the ones below it. But chemically it behaves the same because all of the valence electron spots are filled. Next and final, woo clap question. Sodium, and it's now open. Sodium, which is natrium, hence the Na, has atomic number 11. And it has only one valence electron. Only one valence electron because it's in that first column. Upon losing this electron, what other atom in the periodic table does the sodium now resemble? So what does the electronic structure look like for sodium if you take one electron away from it?
It's not going to say on that table, is it?
It's not going to say no.
I was going to go with this. Is this what you're going with?
Yep.
Okay. Yeet.
I have to reload. What? I'm really deaf right now. I'm too much.
All right. We had 4 that said neon, 1 that said lithium. Now lithium is directly above sodium. It has 1 valence electron, just like sodium. But we took away that valence electrons. It no longer has its valence electron. So it's not going to look like lithium because it doesn't have a valence electron. So we have to look and say, which element on this list has no valence electrons? And the answer is neon. Neon has no valence electrons. Another way that you could have reasonably answered this is, how many electrons does the sodium atom have if it's neutral?
If it's neutral. Sorry, man.
How many protons does the sodium atom have?
What? More than one, less than one. Am I hot or am I cold? Don't laugh.
D6.
11. Atomic number is telling you how many protons it has. And if it's neutral, how does the number of protons relate to the number of electrons? They're the same. So it should have 11 electrons. If you take away one electron, then it's down to 10 electrons. What element has 10 electrons?
Neon.
Yes.
So we got that right?
So 4 out of 5 got it right? Yeah.
Well, you seem kind of disappointed. You should have just been more
So does
excited.
that mean we're gonna get a cookie or a gold star?
Or you're like, I got this.
Cookie or gold star, you'll go with either one.
Yeah. Honestly, yeah.
Yeah.